Alright, welcome back to part 2. In the last video we just looked at creating our values and calculating a few things, our load limit factors and our cruise speed, our design cruise speed and our design dive speed. And then we also looked at our gust alleviation and our reference gust speeds that we're going to use for our gust lines and gust loading. So if you haven't looked at that yet, go back to part 1. And if you're ready, then in this video we're going to look at actually plotting these values and how that'll look. So the first thing, we know that our dive speed is going to be the upper limit of the speed we have to plot. So I'm just going to create a column of just speeds that will calculate all of our load values or load factors at for our various load conditions. So somewhere between 0 and 255 is what we're looking for. I'll plot a bit past that, and I think probably 10 knot increments is sufficient. So we'll just create a column of our speeds, and we'll go up to, let's plot to 270, so we'll go a little bit past our dive speed. I think it fit that all nicely in the window. So our upper design limit load, this is our upper bounds for a balanced maneuver. So this is not including gust loads or anything, and that would be our positive limit load factor. So that's just going to be constant, doesn't matter how fast we're traveling. So that's 2.96 for our aircraft. So that's just going to be equal to cell D17. And it's not going to change. And the lower design limit load, same thing. We now have it minus negative 1.18. And we'll make this constant. So these will just show up as horizontal lines in our plot. So if we're going to plot this, let's insert a plot, and then I'll manually add this information. So I'm going to add them one at a time as we go. So I'll select data, create a new series. Now because this is just a horizontal line, we just need 2 points. I'll pick the starting and end point. Essentially our horizontal axis values are going to be our airspeeds, and our vertical axis values are just going to be constant. So what I can do, we'll do this as n plus, that's the name. Our x values, I guess we could just plot it as normal. Let's try this. Y values, okay, good. So there's a quicker way we could do this then. Let's delete this. Just going to select the whole table, insert, and there we have our upper and lower limit. And then I can go and add the names if I want to, but for now I'm just going to remove the legend. We know what these are. These are positive and negative limits. What I will do is just make them all the same color, so that later on when we're plotting other parameters, let's make this all blue. Let's make those lines thick. It seems like it only let me change 1 point. Don't know why anyone would want to do that. There, so we'll make our positive and limit loads blue, they're thicker lines, and we'll change our title to VN diagram, which is our structural envelope. So our horizontal is our knots equivalent to airspeed, and I left it in knots, so when we get to our gust loads we'll have to convert the feet per second to knots. And then the vertical axis is our load factor, our N. So next thing we need to plot is our stall limits. So our stall lines, we think of plotting your equation for stall. You're rearranging that equation for your weight ratio of lift divided by aircraft weight. So if you do that, you end up with an equation for your positive stall line. That would look like this. So your positive stall line would be 1/2 rho. This is all at sea level conditions. your airspeed, equivalent airspeed squared, times your max lift coefficient. When you're in your stall condition, you're acting at your maximum lift coefficient, maximum angle of attack, divided by your wing loading. So if we plug in this equation for our stall limit line for a positive stall, do the same thing for negative stall, except we'll use our CL min. So that would be, if we had a negative angle of attack, what angle of attack would your wing stall at? So that would be your minimum lift coefficient. So we'll plot this first. 0.5 times density at sea level. So we have that up here. Slugs per feet cubed times our knots equivalent airspeed. Now this is times, for this to be accurate, we need this in feet per second for the units to work out. So we're plotting versus knots airspeed, so I'm going to have to multiply this by 1.688. That brings it to feet per second to make the units work out. Times our max lift coefficient. So let's do our clean wing first. So if you have a clean wing, our max lift coefficient is 1.4 approximately, and then we're going to divide by our wing loading. Our wing loading up above is 30. So just go through and make some of these cells constant. And so now we can add our positive stall limit line and see what that looks like. I'm just going to add positive stall, x coordinates, and y coordinates. Now it's very low, and it looks like it's because I forgot to do something. I forgot to square the velocity term. So that should change it significantly. Yeah, there we go. So we have our stall line for a clean wing for our aircraft, and now it's skewed the scale. We don't really need to look at the scale too far above our positive load factor, so I'm just going to calm this down a little bit. I'll go up to a positive limit of 4 and negative limit of -2, and that will hopefully keep things a bit nicer for us. So that's our positive stall line. I'm just going to copy this over, and we'll do our negative stall line. The only thing that's going to be different now is we're going to have our CL min value. Now, I haven't modeled this, I just assumed a value. If you had a perfectly symmetric airfoil, then your CL min would be equal to your CL max. If you have a cambered airfoil, it's likely going to be less in magnitude. So I chose something that's a little bit less than half, just as an approximation. You can decide that for what your wing would look like. And then we have our negative stall line. So if we do this, we'll add that data as well. Negative stall. X coordinates are our knots equivalent airspeed. Our Y coordinates are our load factors. And we have our negative stall line. So the speed that we didn't calculate before was our maneuvering speed. And our maneuvering speed is defined a couple of ways. It's defined as a minimum. It can't be less than our stall speed times the square root of our load limit factor. But the maneuvering speed in the positive load region would be where our stall line intersects our maximum load limit or maximum limit load factor. So our limit load factor is 2.95. So at the speed where our stall limit is equal to 2.95 would be our positive maneuvering speed, and that would be VA. So maybe if I insert just some text here. I can write this as VA, and that would correspond to the speed. I'll have another line. The speed where we have our stall intersects our positive load limit factor. Hard to talk and think at the same time. So this is our value for VA. Now, if you have a, depending on what your CL min value is for your aircraft, your VG, which is your negative limit maneuvering speed for negative load and maneuvers, would be where the negative stall line intersects your lower design limit load. So that would be called VG. They might be pretty close. They could be somewhat different. In this case, they look like they're pretty close. But let's say I change my CL min value. I'm going to make this negative 0.2. That increases quite a bit. So maybe I'll make it negative 1. And now you can see that they're quite distinct. So maybe this is more realistic for an aircraft or something. We'll use this as an example so we can see more distinctly where these two different lines act. And I'm just going to clean this up a little bit so there's no line and no fill. So there's our value for VA. Copy this over and we have our VG value. These are our positive and negative maneuvering, or our speeds corresponding to our positive and negative maneuvering limits. So essentially what a maneuvering limit means is if I want to pull on the controls as hard as I can, max deflection, max load, if I'm flying below this speed, then my aircraft will not be able to generate the G's to cause damage to the aircraft. It'll just stall instead. So as long as I'm flying below my limit, my maneuvering limit speed, I can do whatever I want with the controls and the aircraft won't be damaged and won't break. If I'm flying above this speed and I yank on the controls, then the aircraft won't stall and I can generate enough G-force to actually cause damage to the aircraft. We'd be flying somewhere up in this region. So we're exceeding that maximum or upper design limit load boundary. So if we want to do maneuvering, for example, if you're in an acrobatic aircraft or a fighter aircraft, you usually have to slow down from a cruise or pursuit speed to a maneuvering speed in order to actually do dogfighting or do aerials. So that's what those two speeds mean. So the next one is, maybe we could just plot our dive speed easily and our cruise speed. Those would just be vertical lines, so we can see where those appear on our plot. Let's do that. So I just want to plot cruise speed, and the cruise speed X value will just be our cruise speed and equivalent airspeed. And I'll just select that point twice. So we have 2 points. And then our Y values, I'm just going to choose -2 and, oh, don't hit the arrow. -2 and 11, so I don't have to deal with it. We've changed our limits. So this is our cruise speed over here, so you can see it's above our maneuvering speed. And then I'll do the same thing for our dive speed. So our X values go up to our dive speed, 225 knots. I want it to be that value twice, comma, and then our value is -2 and 11. Something that's going to exceed those bounds. So I'll move this over here so I can see it. Oh, great. I'll just delete these for now. I'll fix that for later. I'm going to change the color of these. I'll just make them faint. Maybe a bit darker than that. And I'll make them dotted lines so we just see where our cruise speed is. And our dive speed. So we're starting to build up our diagram. We can see sort of our limits. And we need to add our gust lines. So I'll move this over here and we'll look at our gust lines. So I'll just start by plotting our gust load factors for our cruise condition and our dive condition. I'm not going to look at VB right now, but maybe I'll show you how we can add that in for a Part 23 aircraft. So for our cruise segment, let's see, VC, where's our gust information? We have our cruise gust as 50 feet per second, so we need to convert this to knots for our equation. Or sorry, we need to convert our knots over to 50 feet per second in our equation. So let me copy over what that equation was that we can use just so you can see it. And try and find it. So our gust load factor, oh, it's right here. Our gust load factor, this equation right here. So we can just start putting that in. And our design gust velocity is just our reference gust velocity times our alleviation factor K. So this is going to be equal to 1 plus our density at sea level times our velocity. Now I'm going to multiply that by 1.688 to get in units of feet per second times our wing area. Now our wing area is equal to our weight divided by our wing loading. So weight divided by our wing loading gives our reference area times the slope of our CL alpha, or our lift curve, so CL alpha, times, for cruise, our gust velocity 50 feet per second times our alleviation factor kg. Kg is the same for cruise and dive, divided by 2, divided by our wing loading again. So a good check, your first value should just be 1. Your velocity at the beginning is 0, so that second term just goes to 0. We will make all these terms constant that we need, that aren't changing. And so we have our gust load factor. Now this climbs incredibly quick. So perhaps there is something, a mistake. We have 1 plus our density times our velocity in feet per second. Times our wing area times CL alpha. Divided by 2, divided by our wing loading. Let's plot this and see what it looks like. We'll call this gust and cruise. Actually, instead of cruise, God, I hate that. Gust, I'm going to write 50 feet per second so we know the gust velocity. in the actual figure. X coordinates, Y coordinates. Okay, yeah, basically this straight line. So what I'll do, maybe so these videos aren't too long, I'll stop this video here. I'll try and figure out what's wrong, and then we'll finish this up in part 3.